In this video, we are going to discuss intermolecular forces and how that affects the physical properties of substances such as liquids. So unlike gases, liquids do not respond dramatically to temperature and pressure changes. So we talked about how if you have a sample of gas and you increase the temperature, the pressure also increases by a lot. So liquids don't really do the same thing. Now we can study the liquid state and make 5 general observations. So let's go through these. Number 1, liquids have variable shape but a fixed volume. So if you have 100 milliliters of liquid, doesn't matter if you put it in a bowl, in a beaker, in a graduated cylinder, it's still 100 milliliters, but of course it's going to take the shape of the container that you put it in. Number 2, liquids flow readily. So liquids and gases collectively are known as fluids because they flow. However, not all liquids will flow at the same rate. So this has to do with something called viscosity, which we will get to in this video. Number 3, liquids do not compress or expand significantly. So this is important with the braking system or the power steering in your car. So there's tubing that connects the brakes to the braking system and your steering wheel to the tires of your car. And basically there's a liquid in there. And because there's a liquid and it does not compress significantly, the energy, the motion of your foot on the pedal, for example, can get transferred to the brakes. Number 4, liquids have a high density compared to gases, and it's about 1,000 times more dense. So the units for liquids, units of density is typically given in grams per milliliter, but for gases, it's usually in grams per liter. So you can see that that's about 1,000 times, because that milli, that's 10 to the third, or rather like 10 to the negative 3 is milli. But the point is that's a factor of 1,000. Number 5, liquids that are soluble mix homogeneously, so uniform mixing. So soluble, what does that mean? Basically, if things will mix together and blend together, like we could put some sugar in water and it'll dissolve, so we would say that sugar is soluble, but oil and water don't mix. They no mix. So we would say they're insoluble. So liquids that are soluble, they'll mix homogeneously, you'll have a uniform mixture. And then also diffusion, so liquids diffuse more slowly. So if you were to put like a drop of food coloring in the cup of water, the liquid, it'll diffuse but slowly through that beaker of water, but eventually it'll be homogeneous. So intermolecular forces, and this is a really important concept in chemistry just in general. So an intermolecular force, or IMF for short, is an attraction between molecules, and contrast that with intramolecular. So this is inter and this is intra. An intramolecular bond is between the atoms in a molecule. So when we talked about ionic bonds and covalent bonds, those were intramolecular. But this presentation is all about intermoleculars, and we can say IMFs for short. Now, some properties of liquids, such as vapor pressure, are determined by the strength of these attractions. So generally, as the intermolecular forces increase, then other properties increase, and we're going to go through all of those. Now, intermolecular forces are much weaker than intramolecular bonds. So if you were comparing a covalent bond versus just an IMF, the IMF is much weaker than a covalent bond. So a lot more energy is going to be required to break a covalent bond compared to breaking an IMF. So recall that a polar molecule has a positive and a negative charge concentrated in different regions due to unequal sharing of electrons. So that has to do with electronegativity. For example, if we have like a carbon-fluorine bond, carbon is much more electronegative, so it might be a partial negative on that side, and then the carbon is partial positive. So the fact that we have differences in electronegativities, this bond between them will be a polar covalent bond, where we have more of the electrons on the fluorine side and fewer electrons on the carbon side. So this uneven distribution of electrons in a molecule is called a dipole. And intermolecular attractions, or intermolecular forces, result from temporary or permanent dipoles in the molecules. So temporary as in they're fleeting, they're only there for a moment and then they go away, or permanent dipoles where you have a polar covalent bond, like in my carbon-fluorine example. Now, there's 3 important intermolecular forces that you need to know. Number 1 is London dispersion forces, which we very commonly abbreviate as LDFs. Dipole-dipole interactions. I usually say dipole-dipole interactions, but it's the same thing as dipole-dipole forces. And then hydrogen bonding. And hydrogen bonding forces because it's not really a true bond. But let's go through each one. So first up, LDFs, London dispersion forces. They're the result of a weak temporary dipole. So electrons are constantly shifting in a molecule. You have a molecule and there's electrons, the valence electrons, core electrons, and electrons are constantly buzzing around. Why? You take your chemistry classes, you might eventually learn about the Heisenberg uncertainty principle and the Schrodinger equation. The idea is that electrons are bouncing all over the place, and where they are, it's really based on probability. But anyway, a region may become temporarily electron poor, as in few electrons, and slightly more positive, because remember, electrons are negative, while another region becomes slightly negative. So here we have an example of two molecules with just the London dispersion forces, and the green sphere is representing the electron cloud. And then maybe suddenly the molecule on the left decides to be a little bit more negative on the left side and a little bit more positive on the right side, again, because electrons are constantly shifting around. They're not going to be in the same spot evenly distributed all the time. So then what happens is the molecule on the left creates a temporary dipole with its neighbor. So now we got a slightly positive there, and that creates a slightly negative in its neighbor, which also means we have a slightly positive on the other side. So now we've got a very, very weak attraction right here. Opposites attract. And this is the London dispersion forces. We got temporary dipoles that are attracted to each other for the brief moment that the two molecules are polarized. And that's what's happening in these pictures. It's polarization. The molecule on the left became polarized for some unknown reason, just because it felt like it, because the electrons are randomly shifting, and that caused the other molecule to become polarized, and now they become attracted to each other for a brief moment. So London dispersion forces are the weakest of the intermolecular forces. So the three that we listed a couple slides ago, London dispersion forces is the weakest. It is present in all molecules. So if you ever had to list all the intermolecular forces for a substance, you make sure you list London dispersion forces, even if there's others. The strength of the London dispersion forces is related to the number of electrons in the molecule. So if you ever had to explain why the London dispersion forces might be particularly strong or weak, here's your train of thought. So if there are more electrons in the molecule, then it has a larger, more polarizable electron cloud, and thus stronger London dispersion forces. So if we go back and look at this slide, if you had a larger electron cloud over here, then we could have a stronger, or like a more prominent dipole in that molecule because there's more electrons. And then that would create a larger dipole in its neighbor, and then a stronger attraction right in between. But it's all about the number of electrons in the molecule and how big or how fluffy or how squishy that electron cloud is. I like to think of it as the electron cloud is kind of like a balloon, and if you squeeze on the balloon, you'll make it bulge out on the other side, and it could be a balloon filled with air or filled with water, but the idea is that if you have a balloon and you squish on one side, it's going to start bulging on the other side. And that's kind of like how London dispersion forces work with the electron clouds and molecules. Okay, next one, dipole-dipole interactions, or dipole-dipole forces. So polar molecules have a permanent dipole, again, because of that difference in electronegativity. The oppositely charged ends of polar molecules are attracted to each other, and this is a dipole force. And we've kind of got a picture of an example going down there. Now, the strength of the dipole force is typically only 10% of an intramolecular bond, so just like a regular covalent bond. Again, it's weak, but they're generally stronger than London dispersion forces. So London dispersion forces are the weakest, and the dipole-dipole interactions are stronger. And then you can probably guess the hydrogen bonding is stronger than those, so we're going to talk about that next. Now, this picture down below, what we're seeing is a bunch of polar molecules, and the dotted lines are the dipole-dipole interactions. So the negative here being attracted to the positive of this molecule, negative and positive attracted, negative and positive attracted. Those are all the dipole-dipole interactions. Almost like if you had a bunch of magnets, the north and the south would be attracted to each other. It's the same general idea with dipole-dipole interactions and polar molecules. So the last one, hydrogen bonding. It's technically a special type of dipole-dipole interaction. Keep in mind it's not a true bond, so we always call it hydrogen bonding. That's what it's been called over the years, but it is not a covalent bond. Even though we say hydrogen bonding, it's not a covalent bond, so it's not sharing electrons. Now, it's only present when a molecule has a nitrogen, hydrogen, or fluorine bonded to a hydrogen in the molecule. And it's especially important in living organisms because living organisms all have water, and water does hydrogen bonding. So what we're seeing in the picture down here, it's a bunch of water molecules, and the hydrogen bonding that results is between the oxygen of one water molecule and the hydrogen of a neighboring molecule. And that hydrogen must be attached to another oxygen. So it's almost like we're making a hydrogen sandwich where the bread is some oxygen atoms. But you have an oxygen, hydrogen, oxygen right there. And remember, that's the hydrogen bond. These are kind of like ball and stick models. That's a covalent bond. And this is the hydrogen bonding. So now there's 4 physical properties of liquids that we can relate to the intermolecular attraction. So all of these are affected by the strength of the IMFs. And we'll go through each one. So vapor pressure, boiling point, viscosity, and surface tension. The vapor pressure, boiling point, viscosity, and surface tension, all of these are affected by the strength of the intermolecular forces. So first up, vapor pressure, which we talked about a little bit in the previous video. So at the surface of a liquid, some molecules can gain enough energy to escape the intermolecular attractions of neighboring molecules, and this is called vaporization. So this is why molecules will vaporize in the first place, because they just have enough energy to escape the liquid phase, and they need that energy to overcome the intermolecular attractions that they're feeling with their neighbors. Now, the reverse process is called condensation, so that's kind of a review from earlier in the semester. Now, technically, when the rates of evaporation and condensation are equal, the pressure exerted by the gas molecules above a liquid is called the vapor pressure. So that's our definition of vapor pressure, when the evaporation and condensation is the same. So just continuing with vapor pressure, the stronger the IMFs, then fewer molecules are going to be able to escape into the gas phase. So vapor pressure decreases. So as the strength of the IMFs goes up, the vapor pressure goes down. So we got a bunch of examples here, like water as our first example has very, very strong intermolecular attractions because it can do that hydrogen bonding, and hydrogen bonding is the strongest of the 3. And its vapor pressure says 18 millimeters of mercury. Now let's take a look at, how about the ethyl ether? This one has weak intermolecular forces because it can't do hydrogen bonding. It is a little bit polar, but it can't do hydrogen bonding. And notice its vapor pressure is much, much higher. So again, that general trend is as the intermolecular forces, as the strength of them goes up, the vapor pressure, that says VP for vapor pressure goes down. So next up, boiling point. The normal boiling point of a substance is the temperature at which the vapor pressure is equal to the standard atmospheric pressure. So normally we have 1 atmosphere pressure all around us. So what we're saying is if you increase a substance and vapor pressure is proportional to temperature, we saw in the previous video that if you increase the temperature, the vapor pressure goes up. So if you keep increasing the temperature, eventually the vapor pressure is going to be equal to the atmospheric pressure outside, which again, 1 atmosphere on a normal day, give or take. And that's when we say we've reached the boiling point. Now, the stronger the intermolecular attractions, the higher the boiling point is going to be because more energy is required to break the IMFs and boil it. So that is generally what's happening. Anytime you boil something, you have to break these intermolecular forces. Breaking bonds requires energy. So us putting heat into something like boiling water on the stove, you're putting heat into that system, that water. You need to put energy in to break the bonds. What are the bonds you're breaking? You're breaking the IMFs. So you have to disrupt all of those intermolecular attractions. And then, so basically, the trend is as the IMFs increase, the boiling point also increases. And this is opposite of the trend we just saw for vapor pressure. So next up, viscosity. So the viscosity of a liquid is its resistance to flow. So we could have like a lightweight oil like olive oil and compare it to honey. Which one has a hard time flowing out of the bottle? That would be the honey, so it would have a higher viscosity. And viscosity is a result of the attraction between the molecules. So something with strong intermolecular forces would have a very high viscosity. It has trouble flowing. It's going to flow very slowly. And if you have weak IMFs, it's going to flow much more easily. So the greater the attraction, the higher the viscosity. And then last one, surface tension. So the attraction between molecules at the surface of a liquid is called surface tension. So if you've ever tried putting you got a sink full of water, or maybe it's just a puddle on the ground or something, and you try and throw a paper clip on top, if you're lucky, the paper clip will actually sit on it'll float right on the surface, and that's due to surface tension. But to sink in the liquid, it first has to break through the surface. And also the water sliders, little bugs that you just spend their life just floating on the surface. So they're specially designed to just float right on top of the surface due to surface tension. But the stronger the intermolecular forces, the stronger the surface tension of the liquid. So you can get drops of water. If you have a super hydrophobic surface or something, you can get drops of water collecting right on that surface, and they'll form this really cool, perfectly spherical shape if the droplets are small enough, because of surface tension. So it's like the water holding itself together due to the strong surface tension. So structure of water really quick, because again, water is so incredibly important for life on Earth. And the biggest reason is because of the intermolecular forces. So just going to talk really quick about water. It has a bent molecular shape. So when we talked about Lewis structures and Vesper structures, we learned about the bent molecular shape, and it has this bond angle of 104.5. Now in water, each of the two bonds has a dipole. So the covalent bonds right in here between the oxygen and the hydrogen, those are polar covalent bonds, so they have a dipole, and that makes water a polar molecule, and it exhibits very, very strong hydrogen bonding. And again, the hydrogen bonding, so the white dots, that is your hydrogen bonding. So an important skill that might show up on a test is, identify the hydrogen bonding, or, which diagram is showing hydrogen bonding being drawn correctly. Hydrogen bonding is also just kind of like a fun fact. If you ever do a biology class, hydrogen bonding is what holds our DNA together. So we have covalent bonds because there's molecules in DNA, but then the two strands of DNA, if you know about the double helix of DNA, those two strands are held together by hydrogen bonding. So hydrogen bonding in general is very, very important for life outside of the context of just water molecules. Some other properties of water. So water is one of the very few substances that is less dense as a solid. So usually for a liquid, as you cool it down and you freeze it, it goes from liquid to solid, it becomes more dense, but water actually becomes less dense. So this is exactly why you put some ice cubes in your soda at the restaurant. The ice cubes float because the solid ice is less dense than the liquid soda, liquid water. So why is that the case? So as water freezes, the hydrogen bonds organize the water molecules into a three-dimensional structure where they're actually further apart. And you notice the little particle diagram there. We've got this big open space right in the middle. So that's why we've got these air gaps in the crystal structure for water. And so that ends up reducing the density. So liquid water, we usually assume it's 1 gram per mil. Ice actually has a lower density because of those air gaps in the frozen structure. So just to kind of summarize, there's 3 types of intermolecular forces. So London dispersion forces, LDFs, the dipole-dipole interactions, and hydrogen bonding, which, remember, hydrogen bonding, it's not covalent bonding. It's just an attraction between 2 polar molecules. And remember, it has to have N, O, or F. So think that hydrogen sandwich. London dispersion forces are generally the weakest. Hydrogen bonding is generally the strongest. And I say generally because it's very, very easy to find an example where the physical properties are kind of counterintuitive to the intermolecular forces that it's supposed to have. So you could have London dispersion forces that are generally, they're actually stronger in one molecule that has hydrogen bonding because the molecule is just so large, and that gets into that polarizability part. And then, of course, the intermolecular attractions, they affect the physical properties of substances. So, kind of bringing it all together, we learned how to do formulas and valence electrons. And then we used that to create Lewis structures. And then once we understood the Lewis structures, we learned about VSEPR theory, so how to get the shapes of the molecules. Now, VSEPR theory can help us figure out if a molecule is polar or nonpolar, which then that tells us about the IMFs, because London dispersion forces are, for the most part, for nonpolar molecules. So all molecules have London dispersion forces, but nonpolar molecules are not going to have the other forces, dipole-dipole, and hydrogen bonding. And once you know about the intermolecular forces, if they're strong or weak, then you can make guesses or assumptions, or deduce or understand data about the physical properties of substances. So it all ties together. And then just to continue, so vapor pressure decreases as the IMFs increase. So it's an inverse relationship. Boiling point and viscosity and surface tension, however, those all increase as the intermolecular forces increases. So the key one is vapor pressure. It's actually the inverse relationship.